to be analog front end.
Now, we talked about some applications before, right?
Yeah.
But do you know Hall sensors are also used to sense current?
Yes.
Yeah.
I mean, current passing through a conductor.
Current passing through a conductor, as you can see here. Got it. And it's very important in, power electronics, automotive, your smart buildings. Because why? Because by measuring the current, we can measure the power, the energy. Yes.
Yeah. And monitoring.
Condition monitoring. Yes. Good point.
10 number of applications. Yes.
Yes. And this demand for the Hall sensors to be used as, current sensing sensors is also driven by recent trends, right? If you think about trends and policies towards, energy efficiency, right? So very, very important area.
Yes.
Right. But how do we measure the current? I mean, can you measure just like this? Can you just have, let's say you have something like this, right? My drawing is never the greatest, but
it's clear enough. So you are sending some current through that conductor.
Yeah,
this conductor.
I'm sending some current.
So there will be a field produced.
There'll be some field produced. Let's say something like this, no?
Yeah.
There'll be some field produced.
Yeah.
Yes.
Magnetic field.
Magnetic field. So this way means it's going.
And this is calculable in the sense, if this is a current and at a distance from the conductor, this will be the magnetic field.
Exactly.
So if you know the magnetic field, you know the current.
That looks pretty straightforward, right?
And to sense the magnetic field, you are using Hall.
Yeah. Why can't we just put a Hall sensor here?
Yeah.
And this perpendicular.
Yeah.
Where's the current?
Yeah.
That's it.
It is not on the conductor. It's
Sorry. It's not on the conductor, but yeah, exactly. It's not touching it.
Yeah.
It's very close, but one of the biggest problems here is we know that generally, if you are looking at B and D, which is distance away
from the conductor.
Yes.
Goes
down rapidly, right?
Yes.
So this field could end up being very small.
Yeah.
So in fact, you can technically use
this approach.
Yes. But the amount of magnetic field intensity that you can measure is probably not a lot.
So depending on the amount of current flowing through the conductor, also what's the distance from the IC to the conductor.
Yes.
And then we also need to ensure that the gap between the conductor and IC is maintained.
Exactly.
Because this calculation goes as per that.
Exactly. So what's the strategy here then?
So you put a core around it.
Yes. So now what we do is we have a magnetic core here. Okay. So this is still your conductor that has the current flowing, which produces the magnetic field. Now, our students should know this straight away when you talk about cores. Cores, what they do, they confine and guide.
Yeah, it has got a very low reluctance.
Yes.
So the magnetic field will flow through that.
And then it will kind of flow through here.
What's that green thing?
What's that? Is it amplifier?
No. Before that, is it not green?
Oh, this one?
Yeah.
Oh, that's your Hall sensor.
Okay. So you have a small air gap there in that.
Exactly.
Core.
Exactly. So this core is of high permeability, confines the core. That's number one, because that solves the problem we had before, right? Number two, right? There is also a very small gap. So the core is not just one line.
It's a C.
It's a C, right? It's a C like this. Something like this. Okay?
Yeah.
And the flux lines are flowing here.
Yeah. And the Hall sensor is introduced into that gap.
Yes. The Hall sensor is introduced. I mean, if you Yeah. And you have your flux lines here, go around. And here, you'll have magnetic field, and your Hall sensor is then introduced here.
Perpendicular.
Okay. Now, this air gap that we have is actually very small. Is there a limit to this air gap? I mean, do we want it as small as possible all the time? Obviously, the minimum distance has to be equal to the size of the height of the swan.
Yeah.
That's one.
Yeah.
What else? I mean, can you, and then is that the best air gap that you can use?
I mean, it cannot be large air gap. Has to be
It cannot
small.
be too large.
Yeah.
But one of the challenges of using a very small air gap is that your core can saturate at
Low current.
low currents, right? So here, I mean, if you look at the magnetic field here, and here is the current, and these are the graphs for different air gaps. So here, obviously, you can measure a very high magnetic field at low air gaps, but then also it saturates at
It's for a given core material
good
and dimensions.
Exactly, which means that the core material, core dimensions, yes, and core geometry, influence the measurements. Okay.
Now, the previous diagram,
This one.
yeah. So here, I mean, suppose if there is a
This is a bad picture. Sorry. Yeah.
or the IC, we can, I think it's obvious to the students.
Yeah. Something like this.
Yeah.
Better.
So, if there is some other conductor nearby or some magnetic field due to another source, that will also influence. I mean, this IC doesn't know whether it's coming from this conductor or somewhere else.
So you're saying
It's more prone to interference.
Yes.
Interfering magnetic field.
This.
Yes.
Yes. Imagine there's another conductor nearby.
Yeah.
Then what's it going to measure?
Correct.
And if the magnetic field is going to be in the same direction, it will add.
Yeah.
Right?
Add or subtract.
Or subtract, depending on the direction of the current. But this kind of approach, we call it an open loop current sensor. Okay. Now, there are several advantages and disadvantages of this type of.
Why do you say open loop? There is no loop there yet. I can see that.
Sorry?
I mean, open loop because it's just open.
It's open loop because your output is just your output.
Yeah.
It's not.
You are going to put a loop later. That's what I see.
Maybe.
Okay.
Oh yeah, so I forgot to mention. Then you have a amplifier.
Yeah.
This could be like a differential.
Yes.
Any kind of amplifier.
Yeah.
That somehow amplifies the signal.
Yes.
Correct.
Difference amplifier will be.
Yes. So this output, this one it gives a voltage out.
Correct.
Right. That is proportional to the current.
Yes.
That you're measuring.
Yes. Actually, that VH is a small voltage that you are amplifying.
Right. So what we get here is the VH. Right. That is
into
proportional.
gain. Right? VH into multiplied by some gain.
Oh yeah, it's some gain. Correct. Yes. And that's proportional to the current.
Yeah.
Which is what you're measuring here.
Yeah.
Okay. So what are the advantages of this kind of open loop current sensor?
Looks in bit.
Yes, correct. Simple design, low cost, just have a core, right? Low power consumption, small size and width. What are some of the disadvantages, you think, looking at this kind of? I mean, you talked about the interference a little bit.
Yeah. Also, the properties of the core, etc.
Yeah, so let's say core saturation is one.
Yeah.
What about something like temperature?
It will be sensitive.
So that could change the output there.
Yeah.
So
because I think the permeability itself is sensitive to temperature.
Yes. So there could be some errors there, of course, due to temperature. So that's probably one of the disadvantages of that kind of design.